Newton told us what happens when we drop an apple. But what happens when we drop antimatter?
Until recently, we couldn't even make an apple-sized piece of anti-stuff.
Now, scientists are creating anti-hydrogen atoms, trapping them, moving them, and for the first time, we're dropping them.
What they found will change everything you thought you knew about energy, risk, and the future of physics.
If you love bold science that rewrites the rules, hit subscribe and ring the bell. Let's dive into the technology, the danger, and why this moment could be as consequential as the first nuclear pile. For 70 years antimatter existed only as a ghostly byproduct of colliders, brief sparks that vanished the instant they touched normal matter.
But recent experiments have flipped that script.
Researchers produced anti-hydrogen atoms, the anti-version of the simplest atom, and held them in electromagnetic traps for measurable lengths of time. They transported antimatter across campus in portable traps, loaded it onto a truck, drove across borders, and didn't lose a single particle.
That's not just an incremental improvement. That's a technological leap.
Where antimatter was once a nanosecond flash, modern traps hold particles for seconds, minutes, even months. Scientists now store antimatter in battery-powered electromagnetic bottles, containers smaller than a refrigerator that keep antimatter isolated from ordinary matter.
We've gone from blink and you miss it production to stable, portable custody.
That shift moves antimatter from rare laboratory curiosity to something you can ship, study, and, dangerously, think about scaling.
Why should you be alarmed? Antimatter annihilates. When antimatter meets matter, the two convert to pure energy.
The energy density is staggering. Annihilation converts essentially 100% of mass into energy. For perspective, nuclear fission converts less than 1% of mass into energy. 1 gram of antimatter theoretically releases energy on the order of tens of megatons of TNT, orders of magnitude beyond the largest thermonuclear bombs we've ever tested. Even a nanogram, a billionth of a gram, releases energy comparable to several kilograms of TNT. That's no longer just theoretical math, it's why controlling stored antimatter matters.
The scary part isn't speculative, it's practical. Modern traps are portable.
They run on battery backup.
They've crossed international borders.
That means antimatter is not locked away in inaccessible bunkers anymore. It can, in principle, be transported like high-value cargo. Imagine that cargo lost, damaged, or weaponized. Today's safety protocols and containment designs assume accidental release is nearly impossible. But now containment is being tested in everyday environments, on roads, near populations, and across legal jurisdictions. This is a crossroads reminiscent of 1942, when Enrico Fermi assembled the first nuclear pile under a university football field. Fermi proved the principle of chain reactions without knowing whether the same discovery would power cities or level them. Nuclear energy led to both power plants and weapons.
Antimatter is the Fermi moment of a new age.
We've learned how to make it, store it, move it, but we don't yet know how far it can scale or how resilient our containment is under real-world stress.
How do you hold something that annihilates on contact? With fields, timing, and quantum finesse. Magnetic and electric traps suspend antimatter away from any material surface.
Laser cooling brings anti-atoms to near absolute zero so they barely move. Quantum-grade sensors and feedback systems correct tiny fluctuations. Researchers are even manipulating single antiparticles, individual antiprotons, arranging them like atomic Lego with precision that would have seemed impossible a decade ago. Today's labs produce minute amounts of antimatter, but production and storage efficiency are improving faster than many expected. If manufacturing scales, the ethical, military, and economic implications explode. Could antimatter power future propulsion systems or solve energy scarcity? Maybe. Could it enable weapons beyond anything we've seen?
Also maybe.
And because annihilation yields pure energy, the destructive potential for even tiny quantities is unprecedented.
This moment demands urgent global conversation. We need international safety standards for storage and transport.
Transparent reporting of production quantities and containment incidents. Independent audits of portable trap designs and battery backups. Legal frameworks for cross-border antimatter transport and emergency response protocols. Right now, the technology has outpaced policy.
That gap is where accidents, or worse, can happen. This isn't necessarily a doom story.
Antimatter science could unlock revolutionary propulsion for deep space missions, ultra-dense energy storage, and new physics. The same breakthroughs that create risk also offer massive benefits. The point is not to fear progress, but to treat it with the seriousness it deserves. If you want the source notes, experiment timelines, and energy math I used to make this video, check the description. Links to papers and lab reports are there. Tell me in the comments, do you think antimatter will be governed responsibly or rushed into dangerous hands? Like the video if you want more deep science explained clearly, subscribe for weekly breakdowns, and share this with someone who loves big idea science.
Stay curious, and stay careful. Thank you for watching my channel.